Hello, today I'm going to try to derive the Einstein field equations. This will be a basic introduction. It won't be rigorous, it will cover the essence, but it will still be quite complex. If you want more detail, then I refer you to Professor Leonard Suskind's excellent lectures that he gave from October to December 2008 at Stanford. I've put a link to the YouTube version of these lectures in an annotation on this video. I am going to follow his approach so that it will be familiar to you, but I shall do it in a much more simplified version. And let's always remember that it took Einstein 10 years to develop these equations, and he had access to many maths professors on the way. As usual, I'm making the assumption that you understand calculus and basic geometry, and that you've also seen or are aware of the information in my general relativity videos that are already up on YouTube, and in particular that you're aware of two key points. The first is what is called the principle of equivalence, and what that says is that if you are in a box with no windows, then you cannot tell the difference between being in outer space and accelerating with an acceleration g, or being in the same box on the surface of the Earth, stationary, but subject to the gravitational force, which carries an acceleration g. There is no experiment, let's put you in the box, there is no experiment that you can do that will distinguish between those two situations. Now that is actually not quite true. The difference, of course, is that if you are in outer space, travelling with an acceleration g, then all parts of this box, including you, are accelerating at the acceleration g. If you are on Earth, then because the value of g varies according to the height above the Earth, the value of g at this point will be ever so slightly greater than the value of g at this point. And so there is a slight difference in the value of g in this situation. And if you can measure that, then you can tell the difference. That difference is called the tidal force. But apart from that, Einstein said that that was a principle of equivalence. You can't tell the difference whether you are accelerating at g or subject to a gravitational force, which is represented by the acceleration g. The second principle is that light bends in a gravitational field. This was Einstein's reasoning. If you take the person who is in the box that is accelerating through space with an acceleration g, and here is the box, and this time we're going to shine a light from this side of the box to the other side of the box. But of course that will take a finite time, albeit small. And if this box is accelerating with an acceleration g, by the time the light gets halfway across, the box will have accelerated a little bit further forward. So it will now be here, which means the light will have reached that position there. By the time the light gets to the right-hand side, the box will of course have accelerated still further. And now the light, which of course is just going in a straight line, will reach here. So if you look at it, it appears within the box that the light has gone from here to a point lower down to a point even lower down. In other words, the overall impression is that the light has gone from here to here to here, and that's a curve. At least it should be if I've drawn it properly. So Einstein says, if that is what happens when you are accelerating through space with acceleration g, since the principle of equivalence says you can't tell the difference between that and being stationary on Earth subject to an acceleration g, then the same thing should happen in this scenario here, that light will appear to bend in a gravitational field. Now, of course, he could have been wrong. But in fact, this was shown to be true during a solar eclipse. What happens during a solar eclipse is that the moon essentially blocks the sun, so that from the Earth, the sun, as it were, is blotted out. And what was noted from the position on Earth was that they could see a star just slightly to the right of the sun. But they knew, astronomers knew, that that star actually was located behind the sun, and it shouldn't have been possible to see it. And the explanation was that what was actually happening was that light from that star was being bent in the gravitational field of the sun and then coming to us on Earth, giving the impression that the star was here, when in fact the star was really here, but the light was being bent in the sun's gravitational field. Now, here was the problem for Einstein. Newton's law of gravitation, which everybody had thought had served us well for so long, says that the gravitational force is equal to the gravitational constant times the mass of one body multiplied by the mass of another body divided by the distance between them, r squared, or divided by the distance squared. And that's fine, except that in this situation here, light is bending in a gravitational field, but photons of light have no mass. So these two mass terms, well, at least the sun has mass, but the photon doesn't. So this form of Newton's law doesn't work if it is going to apply to light. Photons have no mass. So Einstein came up with a completely different approach to gravity. Instead of there being gravity, he said, actually what is happening is that all forms of motion are represented by movement in curved space-time. And I can illustrate that in this way. Let's suppose that we take a trampoline. This is the surface of the trampoline, and that's representing space-time. And we put a small marble on that trampoline. The marble will have virtually no effect. It might make a very tiny indentation on the trampoline. But now let's suppose I get on the trampoline. Well, if I get on the trampoline with my weight, the trampoline is going to bend quite substantially. And that is the equivalent of bent space-time, or curved space-time. What's going to happen to this marble? Well, the marble is now going to fall towards me. The analogy is not brilliant, but it'll do for our purposes. Now, Newton said that that movement towards me was caused by gravitational attraction. Einstein, on the other hand, says, no, what is happening is the marble is moving along the shortest path in curved space-time. So that when the Earth goes round the Sun, there's the Sun, and here's the Earth in a reasonable circular orbit going around the Sun, Newton says that there's a gravitational force between the Sun and the Earth which provides the centripetal force that keeps the Earth in orbit. Einstein says, no, that's not it at all. What happens is the Sun, being massive, curves space-time, and the Earth is simply going round that curve in a straight line in curved space-time. Now you might be wondering two things. Firstly, what is space-time? And secondly, why did Einstein think that it would be curved? Well, space-time is really just space and time all thought of as one set of coordinates. We usually think of space as having 3 dimensions, which we represent by 3 what are called orthogonal axes. They are at right angles to one another. So we normally have the x-axis, the y-axis, and the z-axis. Or if you like, we have 3 dimensions in space: up and down, back and forth, and side to side. If you add a time dimension to that, you get 4-dimensional space-time. Problem with 4-dimensional space-time is it's very difficult to draw because we can only conceive 3 dimensions. So I'm going to cheat and I'm going to draw 1 dimension of time and 1 dimension of space, which is the x-axis. I could of course draw another dimension this way, but I'll just leave it as 1 dimension of time and 1 dimension of space. Now, if you draw a constant velocity in space-time, you get a straight line. because a straight line is distance divided by time. It's a constant distance divided by a constant time, and that is a constant velocity. But if you accelerate in space-time, you get a curve. The reason, of course, being that acceleration means that the longer the time, the further you go. So there's a curve in the acceleration. And because gravity causes acceleration, it causes a graph which is curved in the space-time coordinates. And Einstein's view was that therefore, in some way, space-time must be curved if it is creating an acceleration which has the effect of creating a curve in those space-time coordinates. Well, that's the end of the introduction, so now it's time to introduce you to the Einstein field equations that we're going to try to derive. And there they are. You may observe that there is only one equation, but in fact that's not true, because you will notice that there are some indices, mu and nu, which arise in several places in the equations. Now, mu and nu represent the dimensions of space-time. 0, 1, 2 and 3. 0 is time, 1 is the x-axis, 2 is the y-axis, and 3 is the z-axis. So mu and nu can each take 4 values between 0 and 3, and the combination of mu and nu means that there are 16 variations of this equation, with mu and nu having numbers between 0 and 3. You might therefore think that there are 16 equations in 4-dimensional space-time, but in fact 6 of them are duplicates, so in fact it reduces to 10. So you are looking at 10 Einstein field equations. Now, what do all these hieroglyphics mean? Well, you'll be pleased to know that some of them you already know. You will know what a half is, you know what 8 is, you know what pi is, G is the good old-fashioned gravitational constant, and C is the speed of light. So there are only a few things that we need to sort out. First, we've got this peculiar term R mu nu, which is called the Ricci curvature tensor. We'll derive that. Then in 2 places we've got this term G mu nu. G mu nu is the metric tensor. We'll derive that. Then we have R, but with no indices. That's called the curvature scalar, and we'll show what that is. Then we've got capital lambda, which turns out to be the cosmological constant, and we'll explain the reason for that. And finally, we've got T mu nu, which is the stress energy momentum tensor, and we'll try to explain what that is. Now, the whole point about this equation is that it balances 2 things. Everything on the left-hand side refers to curvature of space-time. Everything on the right-hand side is to do with mass and energy. And as some people have sometimes helpfully said, that what Einstein field equations basically say is that mass tells space-time how to curve, and curved space-time tells mass how to move. So here's our agenda for the remainder of this video. We've done the introduction. Next, we shall do metric tensors. Then we'll move on to Christoffel symbols, which are capital gamma terms. You may wonder why I need to do that, because they don't appear to feature in the Einstein field equation, but they are heavily involved in the Ricci curvature tensor, so we'll need the Christoffel symbol. Then we'll look at curvature itself, which will enable us to derive the Ricci curvature tensor and the curvature scalar. Then we'll look at the stress energy momentum tensor, and then the cosmological constant, and finally we'll put it all together. You may want to take a break through this video just to collect your thoughts. Indeed, before we move on to the next section, you might fancy a break now. Okay, part 2, the metric tensor. We're going to consider a field. We could consider any field, a magnetic field, an electric field, a temperature field. I'm going to consider one of the most basic fields of all, a field with grass where the cows graze. Here is my field, and it's going to be a very bumpy field. There are hills all over my field, and here am I standing on one of the hills. And the value of the field is going to be the height above sea level. And we usually give fields the value phi. And everywhere you'll agree in my field, there will be a height above sea level that I can measure. And that height will constantly change because my field is a very bumpy field. Now, how do I know where I am? Well, I can impose a set of coordinates. Here's my x coordinate, here's my y coordinate, and I am then at that position on the x coordinate, and that position on the y coordinate. It's a bit like a map reference. So I uniquely define my position, and for every position I take, I can find a value of phi, which is essentially the height above sea level of my position in the field. The question I now want to ask is, how does that height change if I move a little bit? And you should immediately respond that it depends on which direction I move. The reason for that is, let's suppose that part of the field consists of a ridge. Now, a ridge is something where the slope goes down on one side and down on the other side, but along the top it's flat. So if I'm standing on the top of the ridge and I move, let's say this is the x direction, if I move in the x direction I go down the ridge quite substantially. But if I go in the y direction, let's say that's the y direction, I'm just walking along the top of the ridge and that's flat. So direction of movement is important. In the x direction I would drop considerably, in the y direction I stay on level ground. Now, how can I tell by how much the height will vary as I move along? Well, let's consider a gradient. Here is a gradient which I'm going to call a 1 in 10 gradient. What that means is that for every 10 meters that I walk along, I will drop 1 meter. So if I start here and I walk 10 meters, by the time I get to the end, I have not only walked 10 meters along, I have dropped 1 meter down. And the way you would describe that mathematically is you would say that the change in height as I walk along is equal to the gradient, which we express as d phi by dx, the rate of change of height with distance, that's what 1 in 10 is, the rate of change of height with distance, multiplied by the distance you actually walk, dx. Let's just try that for a moment. The change in height will equal the gradient. Well, I've told you what the gradient is. It's 1 in 10. And let's say I walk 5 meters, so that the distance dx is 5 meters. That means that d phi will equal 5 over 10, which of course is a half a meter. So what we've just calculated is that if you walk 5 meters along a 1 in 10 gradient, your height changes by half a meter. But this is the general form. You change in height or change in the value of field is equal to the gradient multiplied by the distance you travel. Now, clearly in my field, I'm not going to have clear gradients like this because it's a very bumpy and irregular field. But over a very, very small distance, which is why I've put dx and d phi, that will be true. But as I said, direction matters. So consequently, one would have to say that the change of height, if you're travelling in the x direction, is equal to the gradient in the x direction multiplied by the distance you walk in the x direction. Or you could also say that the change in height in the y direction is equal to the gradient in the y direction multiplied by the distance you walk in the y direction, which is fine. And these two gradients will not, of course, be the same. If we were on the ridge, this would be a very steep gradient in the x direction, but there would be a level gradient in the y direction. Of course, I may not want to walk in just the x or the y direction. Let's suppose that instead of walking in x or y direction, I want to simply walk in that direction, just to be awkward. Well, of course, that is simply a combination of walking in the y direction and walking in the x direction. And in fact, we can regard these as vectors, and in my video on the manipulation of vectors, I showed that when you want to add vectors together, you do it by a tip-to-tail process, so that in fact you take these two vectors, dy and dx, and you put them tip-to-tail. It doesn't matter which way you do it, so let's take dx is like that, then dy goes the tip of the x vector, matches the tail of the y vector, so this is dx, this is dy, and then the resultant is the tail of the first and the tip of the last. So that becomes the resultant vector, which we'll call ds. And we can use Pythagoras to work out what ds is. Of course, ds squared is equal to dx squared plus dy squared. That, of course, is very simple. If you want to add the vectors together, that gives you, this is the magnitude, but for purposes of adding the vectors together, we simply say that ds, and we put a line above it to indicate that it's a vector, is equal to dx plus dy. Or, if we want to know what the change in height is, we can say that the change in height as we go along the path s is equal to the change in height as we go along the path x plus the change in height as we go along the path y. But these two terms here, dx, d phi x and d phi y, we calculated up here. That's what these two terms say. So I'm going to substitute these values into this formula here. And that will give me that d phi s is equal to, now for d phi x, I'm going to replace that by the gradient times the distance. And here I'm going to replace this by the gradient, but this time in the y direction, times the distance in the y direction. And to be absolutely proper about all of this, what I should actually write is I'm going to give these gradient terms curly d's. And the reason I'm going to do that is because that's what's called a partial derivative. It simply indicates that although this is the derivative with respect to x, there are other derivatives, in this case a derivative in respect to y. It's not the only derivative, so it's called a partial derivative, and it's indicated as a partial derivative by virtue of having a curly d. Now I want to pause for a while I do a nomenclature change, and I promise you it won't hurt. Up to now I have been using the coordinates x and y. I am now going to change them. Wherever I have used x before, I'm going to call that x1. And wherever I have used y before, I'm going to call that x2. Why do I do that? Well, for 3 dimensions in space, we typically use x, y and z as our coordinates. Suppose I needed another coordinate. What letter am I going to use? There isn't one after z. I could, of course, find another spare letter, but letters of the alphabet tend to be used for different purposes in physics, and it can become very confusing. Whereas if I relabel these x1, x2 and x3, if I need another coordinate, it's a piece of cake. It's x4. Indeed, I can even have an x0, which I will actually use for a time coordinate. But if I need further dimensions of space, I can have x4, x5, x6, and so on. There's no limit. So, firstly, changing the coordinates into this system means I've got an unlimited number of coordinates if I need them, or dimensions of space. And secondly, it releases the y system, which I'm going to use for a different purpose a bit later on. So now I'm going to rewrite this equation here in my new coordinates, simply replacing x by x1 and y by x2. They're exactly the same, I've just called them by different names. So if I do that, I will get that d phi, which is the overall change in height as far as my field is concerned, is going to be equal to the gradient, which is d phi by dx, and now that's dx1, times the distance I move, dx1, plus the gradient in the y direction, which is now the dx2 direction, times the distance I move in the x2 direction. And of course I could add further terms, x3, x4, x5, as many as I need. I'm only going to work in 2 dimensions to keep it simple. And I think you'll see that this equation here can be simplified by saying that d phi is equal to the sum over n of the gradient d phi by dn, d phi by dxn multiplied by dxn. When n is 1, you get that term there. When n is 2, you get this term here. And the sum term means you just add them together. So this is a very handy way of summarising the change in the value of field according to all of these values. And you'll notice that n is the summation term. You have to do this for all values of n. Here, I'm only having 2 dimensions. But however many dimensions you have, you need that number of terms. And I'm going to call that equation number, I hope you could see that, let's just write that again, equation number 1. And I'll put a box around it so that when we refer to it later, you'll be able to spot it. Now here comes the general problem with relativity, be it special relativity or general relativity. Any rules that you come up with must be independent of the frame of reference that you're using to make the observation. In my videos on special relativity, which I will refer to during the course of this presentation, we showed that different observers measure different distances and different times depending on their relative velocity. That was called length contraction and time dilation. So if you want to have something that is going to be universally true, you have to make sure that it is true in all reference frames. So when I took my field, where I was standing on the hills, and I put myself at position P, I set a coordinate system which I call the XY coordinate system, but subsequently renamed X1, X2, and I said that was my map reference, X1 and X2, define my position. But somebody else could come along and create another set of coordinates, which we will call Y1 and Y2. And now P, of course I haven't changed my position, I'm still standing on the hill at position P, but as far as the Y frame of reference is concerned, the coordinates are quite different. Y1 and Y2 are quite different from X1 and X2, even though I'm at the same place. And you'll notice that if I want to express Y1 in terms of X coordinates, I have to express it both in terms of an X1 coordinate and an X2 coordinate. In other words, the Y1 position for my point P is actually made up of an X1 and an X2. So the question then that we have to come up with is, if I know all the gradients, which remember we described as d phi by dxn, in the X frame of reference, how can we find all the gradients in the Y frame of reference? And more to the point, how can we relate the two? And for this we use what's called the chain rule. We say that d phi by dy, and I'm going to pick the y1 coordinate. You could pick y2, but I'm just going to pick y1. That is equal, now according to the chain rule, that's equal to dphi by dx1 times dx1 by dy1 plus dphi by dx2 times dx2 by dy1. So you'll notice we're only ever sticking to the y1 coordinate, but we sum over the x2 coordinates, because remember I said that in order to identify the y1 coordinate, you need to know all of the other x coordinates. This can be summarised as dphi by dy, and now I'm going to call this dyn because it could be any, could be 1 or 2 in my two-dimensional system, and that's going to be the sum over m of dphi by dxm times dxm by dyn. Now let's just look at this and compare it to this. What I've done is I've put the general value of n in for y. Here I just had y1, but it could have been y2. You have to pick which one you want. It's either 1 or it's 2. But m is a summation term. You sum over m. When m is 1, you get that term. When m is 2, you get that term. And this is going to be equation number 2, and I'll put a box round that as well. But let me just repeat and emphasise, n is the value you choose. It's either y1 or it's y2. You make the choice. But m is a summation term. You have to sum over all the values of x just to get one of the values with respect to y. Now I want to introduce you to the concept of tensors. We mentioned that when we looked at the Einstein field equations. There were several tensors. What is a tensor? Well, let me start off by talking about a scalar. A scalar is something that has magnitude but no direction. Temperature would be a good example of a scalar. It just has a value, 32 degrees centigrade. A scalar is what's called a tensor of rank 0. Now consider a vector. A vector, of course, has magnitude and direction. So it has a length and it has a direction, which is often described as the angle to one of the axes, in this case to the x-axis. And a vector is described as a tensor of rank 1. And how does a vector transform? Well, we can use equation 1 that we derived earlier and which is showing on the screen, so you recognise it, and we just make a slight adjustment to it so that instead of dphi and dx, we replace it by the vectors themselves. So we would simply say that the vector in the y frame of reference and with the coordinate n, which we choose, is equal to the sum over m, where m is now the summation term, of the, as it were, gradient, which is dyn over dxm, where m is the summation term, times the vector in the x frame of reference, m. So that is the way in which we, and I shall call that equation number 3, that's the way vectors transform. We're using equation 1 that we derived and modifying it slightly, that the vector in the, or rather the nth coordinate of the vector in the y frame of reference is equal to the sum of this gradient term times the mth, where m is summed, of course, coordinate in the x frame of reference. And you have to sum over these terms in order to get the nth coordinate in the y frame of reference. The tensors that we will be interested in are tensors of rank 2. And what a tensor of rank 2 is a combination of vectors where there is a fixed relationship between the two. So let's just think of some system which has a combination of vectors. Let's take a very simple one. Let's put a block on the floor and we're going to apply a force to it in order to move the block a certain distance, x, in this direction. And the work done will be the force times the distance. But of course we can't just take the force, we have to take the component of the force that is moving in the direction we want to go. So if that angle is alpha, then the component of the force acting in the direction of movement is F cosine alpha. So the work done will be the component of the force that's in the direction we want to move times the distance we travel. And you can think of F and X as being vectors. X has a magnitude and a direction. The direction is in the X direction. F has a component that has a magnitude and a direction. The component, at least, of force in the X direction. It has magnitude and direction. So we've got essentially something which combines two vectors. Now, the question is, suppose the force is in that direction. Then the angle alpha will be 90 degrees and the cosine of alpha is 0. And therefore the work done will be 0 because, of course, the block won't move. If you're pushing down on the block, you're not going to get it to move in the X direction. And here's the thing, that it doesn't matter what frame of reference you apply to this system, whatever frame of reference you apply, that block will not move. The value of the work done will be 0 in all frames of reference. And that's the value of a tensor. A tensor is the relationship between two vectors. And if the tensor has a value of 0 in one frame of reference, it must have a value of 0 in all frames of reference. If that block doesn't move, it doesn't move. It doesn't matter what frame of reference you apply to observe it, it doesn't move. Tensors, therefore, are fixed relationships between two vectors in such a way that if that relationship equals 0 in one frame of reference, it equals 0 in all frames of reference. And that is why tensors are so important in Einstein field equations. So let's consider a combination of vectors. Doesn't matter what it is for these purposes. We're going to take vector A and we're going to take the nth coordinate of that vector. Remember, there are dimensions in space. I am actually using only 2 dimensions for this simplistic analysis, so m is either 1 or 2. You choose which one you want it to be. And we take another vector B and we'll take the nth coordinate. That can be 1 or 2, you choose. And we say that the combination of the two becomes a tensor of rank 2, which we indicate by saying that it has those 2 coordinates, m, or 2 indices, m and n, equals the vector A with the coordinate or the dimension m, and vector B with the nth dimension. So obviously, if I'm talking about 2-dimensional space where m can be either 1 or 2 and n can be 1 or 2, then Tmn, there can be 4 versions of that tensor, where m and n each have values 1 and 2. If you've got 3 dimensions of space, m and n can each have values 1 to 3, and so Tmn has 9 different versions. If there are 4 dimensions of space-time, 1 time 3 dimensions, Tmn will have 16 different values. Well, now I'm going to use equation 3 that we derived earlier and which should be showing on the screen to take the vectors A and B. So we're going to take AM in the Y frame of reference and BN in the Y frame of reference. And we're going to try and see what they are in the X frame of reference using equation 3. Well, you can see that we've just got to replace v in equation 3 by a and then b. So let's do a first of all. We need a sum term. I can't use m anymore because that's already been used here. So I'll just introduce a value r. Remember, this is a summation term. It's called a dummy variable. It doesn't matter what you put. And that's going to be dym by dx r times a in the x frame of reference r. That does the vector a. And now we need to do the vector b in the x frame of reference, which again from equation 3 comes, I now need another summation term. Let's call it s. And that's going to be dyn by dx s times b in the x frame of reference s. So you sum over the r terms and you sum over the s terms, but m and n are chosen. They're the values you happen to choose for this particular equation. Well, let's look and see what this reduces to. Firstly, ambn, well, that's just the tensor tmn in the y frame of reference, because that's what we selected here. And that is going to be equal to the sum over r and s. That's not quite the right way to do it, but essentially you've got two sum terms here, which I'm just going to simplify here, multiplied by dym by dxr, and then you've got a dyn dxs times axr bxs. That's that term and that term. But what is this? Well, if you look at this term up here, you'll see that it's just another tensor. In this case, it's the tensor in the x frame of reference, but its indices are r and s. And that I'm going to call equation 4. And I'll put a block round that because we may need that in the future. And that is called, it gets a technical term, it's called the contravariant transformation. It's the transformation from the y frame of reference to the x frame of reference for tensors. There is an equivalent form of tensor transformation that is called the covariant transformation, where the indices, which instead of being upstairs, go downstairs, but then the dy by dx terms are changed into dx by dy terms. So let me just write that out. You get the t, and now it's in the y frame of reference, but the m and n go downstairs. So I'll put the m and n down here, and to make it clear, I'll put y in brackets. So tmn in the y frame of reference are equal to, again, you've got this summation term over r and s. And now these two terms just go upside down, dxr by dym, dxs by dyn, just inverting these terms here. And then the tensor term, again, goes downstairs, but it's in the x frame of reference. And that is called the covariant transformation. And I'm going to call that equation number 5. So this is called the contravariant. This is called the covariant. Contravariant have the indices upstairs. Covariant have the indices downstairs. Contravariant have dy by dx terms. Covariant have dx by dy terms. And it is actually the covariant form of transformation that is going to be of interest to us. Now I want to do a little bit of manipulation with something as basic as Pythagoras. Pythagoras applies to a right-angled triangle, and if this is dx1 using our frame of reference in the x frame of reference, and this is x2, this is ds, the hypotenuse, then of course you can easily say that according to Pythagoras, ds squared is equal to dx1 squared plus dx2 squared. And if there were further dimensions, you would have it plus dx3 squared and so on. And you'll agree, will you not, that that is simply the summation over m of dxm times dxm. In other words, when m is 1, you get dx1 squared. That's that term. When m is 2, you get dxm is 2, dx2 all squared. That's that term. If m were 3, you would get a further term, dx3 squared. Now I'm going to make it a little bit more complicated, but you'll see why, of course, in a minute. That means that ds squared is equal to the sum over m and n, what am I doing, of dxm times dxn. Now you will say, no, that cannot be right, because there is no combination of dx1, dx2 in Pythagoras. There is only dx1 squared and dx2 squared. If you do this, you're going to get a dx1, dx2 term, and we don't need it. Perfectly true. So we add a further term, which is called delta mn. And that term is called the Kronecker delta. And the thing about the Kronecker delta is it has the value of 1 if m equals n, and it has the value of 0 if m does not equal n. So when m equals n, then you simply get the squared terms that you want. When m does not equal m, then this whole term becomes 0 because delta mn is 0. So if m does not equal n, all the cross terms come out. And we'll need that approach. It's a very complicated way of describing Pythagoras. Delta mn, remember, is the Kronecker delta. It equals 1 if m equals n. It equals 0 if m does not equal n, and therefore avoids any of the dx1, dx2 terms that you don't need in Pythagoras. So I've rewritten that formula that we just derived. I've simply put the Kronecker delta at the beginning rather than at the end. It doesn't matter where it goes. And now I want to remind you of equation 1 that we derived and which should be on the screen. And I'm going to rewrite that in a slightly different form. I'm going to say that dxm is equal to dxm by dyr times dyr. And you'll notice that the difference is that instead of phi in equation 1, I've used xm. Instead of using n as the dummy summation term, I've used r. And I've changed round the x and y coordinates. There's no reason why I shouldn't do that. So now I'm going to take the value of dxm, which is this, according to equation 1, and substitute it in this equation here. And then I'll do the same for dxn. So what I'm going to get is that ds squared is equal to delta mn, which is this term here, plus the summation term, which we don't need to worry too much about. Einstein actually dropped it. He said it was implicit. He didn't even bother to put it in. But I'll just keep it there to show that there is a summation going on. And then instead of dxm, I'm going to put this term here, which is dxm by dyr times dyr. And then we're going to multiply by dxn, which I'm going to put the equivalent version here, which is going to be dxn by dy. I now need another summation term, call it s, times dys. So this term is simply this term equals this. This term is this term modified equals this. And now I can rearrange that so that I can say that ds squared is equal to delta mn. We need a summation term. Let's just bring the two gradients together, dxm by dyr, dxn by dys, and that leaves us these two terms here, dyr, dys. And that's, as it were, a form of Pythagoras. But this term here is called the metric tensor. It's Gmn. And if you look, you'll see that there's an equivalence with what we derived up here as Pythagoras. Pythagoras was simply the summation term with a Kronecker delta, which made sure you didn't get any cross terms. Here we've got exactly the same thing. We've got ds squared is equal to a combination of these two elements here. But instead of having just a simple Kronecker delta, we've now got a more complicated metric tensor. So we can now write that ds squared is equal to the metric tensor gmn times dyr dys. And of course there's a summation. Gm contains a summation term. For flat space, it's pretty obvious that gmn is simply going to reduce to the Kronecker delta term. That should be dmn, delta mn. So it will be 1 when r equals s, and it will be 0 when r doesn't equal s. So for flat space, the metric tensor will either be 1 or 0, depending on whether r equals s or not. But here's the rub. Suppose you aren't in flat space. In flat space, it is perfectly true that if that's dx1 and dx2 and that's ds, it is true in flat space that ds squared equals dx1 squared plus dx2 squared. That's Pythagoras in flat space. But that is not true if you take a sphere and you try to draw a triangle on the surface of a sphere, on the surface, then this formula, which we derived, which is just plain Pythagoras, that is not true on the surface of a sphere. And how do you make the correction for that surface? You make the correction by introducing this metric tensor. So if you like, you can think of the metric tensor as the device which makes corrections to Pythagoras when you have got the right-angled triangle on a curved space instead of a flat space. So you can begin to see the value of the metric tensor if we're going to talk about curved space-time. So here is the Einstein field equations, or here are the Einstein field equations, and the g mu nu terms are the metric tensors we just derived. Why have they got mu nu instead of mn? The answer is that you use mu nu when you also include space-time. What I just derived was solely associated with space, m and n. If you want to introduce time as well, then you say mu nu, where mu can now be either 0, which means that's the time component, or 1, 2, 3, which are the 3 space components. So that is the metric tensor, and you may now like to take another break. Okay, we now proceed to part 3, the Christoffel symbols. Now you'll remember that I said that the important thing about tensors was that they represent a fixed relationship between two vectors, and they are independent of the coordinate system. In particular, if one tensor is 0 in one coordinate system, it will be 0 in all coordinate systems. So let's suppose that we have a tensor, let's call it W, and we'll take the n and mth coordinates in the x frame of reference, and we'll say that that is equal to another tensor, also with n and m coordinates in the x frame of reference. If that is true in the x frame of reference, it must be true in all frames of reference. To take my example of the field right at the beginning, if the height of the field is 2 meters, it matters not what frame of reference you're talking about. It will always be 2 meters. But here's the problem. The problem is that the derivatives of tensors do not necessarily transform between frames of reference, and we're going to need derivatives of tensors. So we need to know what goes wrong. So let's take a tensor in the x frame of reference, which we'll call Tmn, in the x frame of reference. And let's say that that equals the derivative of a vector v with respect to n in the x frame of reference. Now the question is, does that same tensor in the y frame of reference equal the derivative of the vector m with respect to y in the y frame of reference? Is that true? And the answer is no, sadly, and we'll find out why. I'm going back to equation 5, which should appear on the screen, but I'm just going to rewrite it exactly as it was, that the tensor Tmn in the y frame of reference is equal to dxr by dym times dxs by dyn times trs in the x frame of reference. That was just equation 5. I dropped, you'll notice, the summation term just as Einstein did. The s and r terms are dummy variables. You need to sum over them. But let's drop the summation term. Well, let's just rewrite that. That is going to be, I'm just going to rewrite these terms here. dxr by dym times dxs times dyn. But instead of trs in the x frame of reference, I'm going to use this term here. But of course, I'm going to change m and n to r and s. So this now becomes, from the equation above, dvrx divided by, or as it were, with respect to dxs. I've simply written trs in this form here, a dv by dx term. Now, if you look at that combination of terms there, you've got what is essentially the inverse of the chain rule. This is a dxs term, this is a dxs term. You can, in a sense, contract this, so it simply becomes dvr by dyn. And so you get that tmny, which is what we're trying to calculate, so tmn in the y frame of reference is equal to this term here, dxr by dym, times this contracted, which is just dvr by dy, so this is dvr in the x frame of reference divided by dyn. And the question we want to ask is, does that equal dvm by dyn in the y frame of reference? So does it equal question mark, does it equal, because we don't know whether it does, dvm in the y frame of reference by dyn? Well, what is this term dvm by dyn? Let's just write that out, dvm by dyn. I'm going to use equation 5, which is actually a tensor term, but remember, tensors you can reduce to vectors just by dropping one of the indices, and if you just do it for a single index, then you can see that dvm by dyn is actually equal to the derivative of, with respect to yn, of dxr by dym times vr in the x frame of reference. That is what dvm by dyn is if you take it from equation number 5, but looking at it only with one index. But this is a differentiation of a product. And you should know that if you differentiate a product, let's differentiate A times B, then the differential of a product will be A times dB plus B times dA. So if this is A and this is B, then the differential of that, differential of AB will equal, so we've now got that dvmy by dyn, which is this term here, is equal to AdB, which is dxr by dym, times dB, which is dvr in the x frame by dyn, that's dB, plus B, which is vrx, which will stick out here, times dA, which is the combination of these two differentials. So we've got d by dyn times dxr by dym. That's that combination there. Now, observe that this term here is equal to this term here. Tmny equals that term there. And we were asking, does that term there equal this term? And this term equals, yes, we've got exactly the same answer that we wanted. Those two are exactly the same, except there's an additional term here. So actually they are not equal. We've got this additional thing here. And that combination of differentials, just that little combination there, is called gamma, capital gamma. It's actually given the title the Christoffel symbol. And we represent the indices that appear here by putting, since there's an R upstairs, we'll put an R upstairs, and since there's an N and an M downstairs, we'll put an N and an M downstairs. So that symbol, that Christoffel symbol, that capital gamma, is simply a shorthand way of writing this double differential there. It's the extra term that says that those two things are not equal. In other words, let's just make it clear, what we asked was, does Tmn in the y frame of reference equal dvm by dyn? And the answer was, no, it doesn't, because there's that extra term. And the way we get round that extra term is we say that Tmn y does equal a new concept which we will call the covariant derivative, that's what that symbol means, of Vm. So it's not the ordinary derivative, we've shown it was not. We're going to call it the covariant derivative. And what is the covariant derivative? Well, the covariant derivative is going to be the ordinary derivative, dvm by dyn, which is what we thought it was, but it wasn't, plus the Christoffel symbol, plus the correction term, multiplied by vrx. And so we've now got a transformation where you've got derivatives, which has to include this Christoffel symbol. It's the extra term. And I'm going to call that equation 7. So let's put a box around it. And now we can ask ourselves the question, so what is this Christoffel symbol? And it's the compensation for the fact that the ordinary derivative of a tensor in one frame of reference does not transform. You need the covariant derivative in order that you can get a transformation of a derivative of a vector which is a part of a tensor. And that's important because a lot of the Einstein field equations require derivatives of tensors. Well, we just did that using vectors. We're going to need to expand that for the purposes of tensors. So let's take the covariant derivative I'm going to have to use p because I'm going to use m and n in a moment, because I'm going to do the covariant derivative of the tensor Tmn. And that is going to be, if you look at the equation that we just derived, which is equation number 7, showing essentially if I double that up for two indices, I'm going to get the ordinary derivative, Tmn by Typ. You can see how that derives from equation 7. But now I'm going to need two Christoffel symbols. So I'm going to need one for the m element and one for the n element. So this is going to be plus another Christoffel symbol for the n element, and that's the transformation of a tensor from one frame of reference to another. And we'll call that equation number 8. Now, what about the covariant derivative of the metric tensor that we derived earlier? Let's just remind ourselves what the metric tensor was. We started off with good old Pythagoras, where this was dx1, this is dx2, this is ds, and we said that ds squared equals dx1 squared plus dx2 all squared. And we said that you could rewrite that as the sum of dxn times dxn. Or if you like, you could write that as the sum of dxm dxn times the Kronecker delta mn, where, remember, the Kronecker delta was 1 when m equals n, and it was 0 when m does not equal n. And we said that on flat space, that is essentially gmn for flat space. It's not true for curved space. Indeed, that's the reason you have the metric tensor gmn. It corrects Pythagoras for curved space. Now, what is the derivative? We'll call it the covariant derivative of gmn, let's say with respect to r, in the x frame of reference, if we are talking about flat space. Well, in flat space, the metric tensor is either 1 or it is 0. It is a constant. So the covariant derivative of a constant in flat space is 0. But what did I tell you about derivatives of tensors? If you've got a value of 0 in one frame of reference, then you've got a value of 0 in all frames of reference. So consequently, the derivative of the metric tensor will, or the covariant derivative of the metric tensor will equal 0 in all frames of reference. Which means if we take this formula up here, equation number 8, and replace, just write it out again, but put put g in place of all the t's, we will have a transformation or a value of the covariant derivative of g in terms of all these terms, but the covariant of g, of course, always equals 0. So if we replace t's by g's, then this all becomes 0. So let's just do it. I'm going to take equation number 8, and I'm simply going to write it out again exactly as it was, but this time I'm going to substitute g for all the t's. So I'm going to get dgmn by dyp plus the Christoffel symbol pm and r of grn plus the Christoffel symbol pnr of gmr. And what I can now tell you is that the covariant derivative equals 0. So I can put that as 0. And now I've got an equation which has got the metric tensor in it and a derivative of the metric tensor and a Christoffel symbol. So I ought to be able to rearrange that equation so that I can express the Christoffel symbol in terms of the metric tensor. Now for that, you need a mathematician. So you go along to your friendly mathematical professor, and I dare say Einstein did the same, and he will tell you that if you've got a Christoffel symbol with just A, B and C, then that is going to be equal to, take a deep breath, a half GAD, where D is an additional term, it becomes an additional summation term, into the derivative of GDC divided by dxb, or by dxb, plus, remember the mathematicians come up with this, so we naturally take their word for it, minus, hope this is going to fit in, dgbc by dxd. And I'll call that equation 9. And what you've got, courtesy of the mathematicians, is you've taken this term which we ourselves managed to derive, you've jiggled it about so that you've got, because it equals 0, you've got the gamma terms, the Christoffel terms, expressed in terms of the metric tensor and first derivatives of the metric tensor. So what can you say about this Christoffel symbol? Firstly, it's not itself a tensor. It's, in a sense, it's a correction term. Christoffel symbol will be equal to 0 in flat space. But it won't be equal to 0 in curvilinear time space, or space-time. And you'll also notice that it can be expressed wholly in terms of the metric tensor and the first derivatives of the metric tensor. And you might ask yourself, why have we spent all this time trying to find a thing called a Christoffel symbol when it doesn't even feature in the Einstein field equations? You will not see a Christoffel symbol in that equation or those equations. And the answer is no, you won't. But that's because the Christoffel symbol is buried in the Ricci curvature tensor. And that's what we're going on to next. But first, I think it's possibly time for another break. Okay, so now we come on to curvature. If we're going to talk about curved space-time, we better understand what curvature means. Let us take a path in flat space or flat space-time. My paper is flat. What you do is you take a vector. A vector, of course, will have magnitude and direction. And what you do is you what's called parallel transport it around the path. That means you keep the same length of vector and you keep it oriented in the same way, so it travels parallel to itself. So all of those lines are intended to be, my drawing may not make it quite so obvious, but they are intended to be the same length, and all of the vectors are parallel, so they just keep parallel to themselves until you get back to where you started. And of course, when you get back to where you started, your vector will be of the same length and it will be in the same direction because it's always moved parallel to itself, so it will come back to where it started. Okay, all very well and good, but now let's take a cone. Here is a cone which I have made for illustration purposes. As you can see, it's a curved cone. But what I can do is I can cut down the side of the cone and open it up. So if I make a cut along one line, I can then open the cone up and it becomes flat and it has that kind of shape. So let me recreate the cone. I just bring those two lines together. When it's a cone, that edge is joined up. So in a sense, this edge here and this edge here are the same line, the same point on the cone. So let's just draw what the cone looks like when you open it up. You cut down this point here and you open it up and you get a shape that looks like it's a circle but with a slice taken out of it. That's the cone. Just a quick reminder, there it is, the cone. And remember that the line OA and the line OB, when they are in a cone, are the same line. It's that dotted line. Now I'm going to do a bit of parallel transporting, and to remember where the vector was, let me just take that B out of the way and put it there, AB. I'm going to have a vector which continues the line OB. So it's just a straight continuation. And now I'm going to parallel transport that vector around the cone. Remember, it stays the same length, though mine may not. It always stays parallel, and we keep going until we get to A, and we stop because A is point B. Remember, they are the same points on the cone. But what has happened? Well, the length of the vector is the same, but the direction of the vector has changed. You can tell it's changed direction because I started it as being an extension of the line OB. And OB is the same as the line OA. Remember, it's this dotted line here. So if the vector were to be in the same direction, it should end up like that. But it didn't. It ended up like this. It's gone through an angle. So although the length has remained the same, the direction of the vector has changed. And that is a measure of curvature. If you parallel transport a vector around a surface and you don't get back, you get back to the same position, remember position A is position B, you get back to the same point, but the vector has changed direction, then you've gone round a curve. So that's how we're going to define curvature. An angle change in the vector when you parallel transport it around a surface. If it's a flat surface, as we showed, no change in direction. If there's a curved surface, it changes direction. Now I'm just going to take a slight diversion and a pause to deal with two definitions. The first is what's called a commutator. Commutators are written like this, square brackets, A and B, and all that means is AB minus BA. A times B minus B times A. Now, of course, if we are simply talking about pure numbers, then that will equal 0. 3 times 2 minus 2 times 3 is 0. But the point about commutators is they don't always equal 0. And I'm particularly going to look at 1, which is the commutator of d by dx and some function of x. That's my commutator. And I'm going to show that that actually equals dfx divided by dx. It doesn't equal 0. So let's just do the quick proof. Remember that the commutator is AB minus BA, so it's going to be that times that minus that times that. So let's just write that out. That's going to be d by dx of fx minus fx times d by dx. Now you've got to apply a d by dx to something, so let's just call it v. But here we've got the differentiation of a product, and just as we did before, we can say that DAB is equal to BDA plus ADB. Doesn't matter which way round you do it. Differential of a product, BDA plus ADB, where this is A and this is B. So consequently, this term here, using this formula here, will equal B, which is V, times dA, which is dfx by dx, plus A, which is fx, times dB, dv by dx. And that's that term, and we must remember that term there, which is minus fx dv by dx. And you'll see that that term and that term are equal, so one minus the other is 0, and you're left with v times dfx times dx. Well, v is something we simply inserted, so we can now take that out, and now you've got that the commutator is equal to dfx by dx, which is what we wanted to show in the first place. So let's now take two coordinates, which do not necessarily have to be at right angles. This is the x mu coordinate. This is the x nu coordinate. And I'm going to have a distance, which I'm going to call dx mu. And I'm going to have a distance this way, which is dx nu. So a distance dx mu in the x mu coordinate system, and a distance dx nu in the x nu coordinate. And what I'm going to do is construct a parallelogram from that. So essentially it's going to be a parallelogram where the length of these two are going to be dx mu, and that's the same there, and the length of these two sides dx nu. So far, so good. And now I'm going to do a parallel transport around this path. We're going to go from A to B to C to D and back to A again, but I'm going to call the return point A prime, because I'm not sure that we're going to get back, the vector will be exactly the same when it gets to A prime. So the vector at A prime may not be the same as the vector at A if we have gone round a curved surface. Now let's just take two paths, consider two paths. The first is VC minus VD. That's essentially what we're talking about there is the difference between the vector at point C and the vector at point D. And compare that with the vector at point B and the vector at point A. Now, if we are going around a flat surface, then VC minus VD will equal VB minus VA, and that whole term will equal 0. But what this is actually representing is the differences in the d mu direction, because that's the or dx mu direction, because that's the directions that we're moving here. Similarly, if you take VC minus VB, which is this path here, minus VD minus VA prime, you get the difference in the dx nu direction. Because that's that path there and that path there, they're parallel. In flat space there would be no difference, but in curved space there might be, and you're now looking at the difference in the d nu direction. Now let's have a look at the difference of the differences. If we take this term here and we subtract from it this term here, what do we get? Well, let's have a look at the VB term. We've got a minus VB and a minus minus VB. That becomes plus, so we get a minus plus is 0. We get no resultant VB term. Let's look at VC. We've got a plus VC minus VC. The VC term goes. VD, we've got a minus VD minus a minus VD, so it's plus, minus plus. The VD term goes as well. What about VA? We've got a minus minus, so that becomes a plus. So we've got VA, and then we've got for VA prime, we've got a minus minus minus. So 3 minuses make a minus, so that becomes minus VA prime. And that's the difference of differences. That's going to be the change in the vector as it is parallel transported around that parallelogram. As I say, in flat space, no problem. dv will be 0 because there won't be any change. It will just parallel transport round. It will come back to the same magnitude and the same direction. But if it's in curved space, there will be a difference, not in length, but in angle of the vector. Now let's take this first term here, vc minus vd. What actually is that? Well, that is the change as the vector goes from c to d along a distance dx mu. So vc minus vd is simply the change in the vector along the distance x mu. That's the gradient, multiplied by the distance you travel, which of course is dx mu, multiplied of course by the vector itself. So what we're saying is that the change in the vector between c and d is the gradient. Remember, we did this right at the beginning with our field. The gradient multiplied by the distance times, of course, the value of the vector. But we've just learnt that we need to be very careful about ordinary derivatives when you're talking about curves. You need to use the covariant derivative. So actually, to be more accurate, we better call this the covariant derivative. So instead of using this gradient, we're going to use the covariant derivative times dx mu, that's this term here, times the value of the vector. That's a much healthier way of doing it because we've just learnt that you have to be very careful about ordinary derivatives when you're transforming between different reference systems. Now, what is this term vc minus vd minus vb minus va? That is the difference in the differences on a line which is separated by the distance dx nu. So essentially what you're doing is you're looking at the difference of vectors with a separation of dx nu, which means you have to apply a new gradient to it. So vc minus vd minus vb minus va, which is this term here, which is, as I said, the difference in the vectors in those two lines separated by a different distance dx nu. Well, we said that vc minus vd is the covariant derivative times the distance times, oh that's, sorry, not nu, that is v, times the value of the vector. But the difference is essentially another differential, and it's the differential in the new direction. So we've now got to add covariant derivative in the new direction times the distance away. So that is effectively what that difference equals. What about this one here? Well, this one will just be the opposite. In other words, vc minus vb minus vd minus va prime is just going to be, well, vc minus vb will be the covariant derivative, but this time in the new direction. So now we need covariant direction in the new direction times dx nu times the value of the vector. But this subtraction means that you're looking at the difference between this line and this line, separated by dx mu. So you're essentially applying another differential, but this time in the mu direction. So we've now got that term is essentially that term, and this term is essentially this term. And what we said was that if you subtract that, or if you subtract that term from that term, you get va minus a prime, which is the difference in the vector, the difference between the vector at the starting point and the vector at the end point. So if you subtract this term from this term, you're going to get dv, the difference in the vectors. So let's write it out. dv is going to be equal to that term minus that term, which is gamma nu, covariant derivative nu, covariant derivative mu, doesn't matter which order we put these in, dx nu dx mu v, minus this term, covariant derivative mu, covariant derivative nu, dx nu v. And we can pull out the dx mu and v because order again doesn't matter here. So that becomes dx nu v into what's left, which is covariant nu covariant mu minus covariant mu covariant nu. And that you'll recognise, of course, is simply the definition of commutator, which is, of course, simply delta nu comma delta mu. Not deltas, covariant derivatives of. But you'll remember that from equation 7, the covariant derivative is equal to the ordinary derivative. Incidentally, when I write d nu like that, what I really mean is d by dx nu. It's just a shorthand. Plus a gamma term. I won't write out the full details of it, but there was a gamma term. Remember, that was the correcting term, the Christoffel symbol term. So wherever we have this covariant form, we remember from equation 7 that the covariant form is the ordinary derivative plus this correcting term, which involves the Christoffel symbol. So on that basis, the commutator of which we identified before is going to be equal that times that minus that times that. That's what a commutator is. But remember that the covariant derivative is the ordinary derivative times the, plus the Christoffel term. So we now get that that is equivalent to, well, this term is d nu plus the Christoffel symbol associated with nu, times this term, which is the d mu plus the Christoffel symbol associated with mu, minus this term, times this term. I hope you can see that. And let's just multiply that all out. So we've got a d nu times d mu term. Then we've got a gamma nu times d mu. Then we've got a d nu times gamma mu. And finally we've got a gamma nu gamma mu. And that's that all multiplied out. From that we have to subtract this term. Well, let's multiply that out. We've got a d mu times d nu. Those should be curly d's, by the way. All of these should be curly d's. Plus, we've got a d mu gamma nu term. Then we've got a gamma mu d nu term. And finally, we've got a gamma mu gamma nu term. Right, let's do the subtractions. d nu d mu minus d mu d nu is equal to 0 because for ordinary derivatives the order doesn't matter. Gamma nu d mu minus d mu gamma nu, well, that's a commutator. In fact, that is equal to the minus the commutator of d mu gamma nu. Gamma nu d mu is equal to minus the commutator of d mu gamma nu. We've got another commutator here, d nu gamma mu minus gamma nu d nu. Well, that's just the commutator of d nu gamma mu. And then we've got gamma nu gamma mu minus gamma mu gamma nu, and that again is going to be the commutator of, gamma nu gamma mu. So just remind you, that was the commutator of the two covariant vectors here, or two covariant terms here, becomes this term here. But you may remember when I took that diversion to talk about commutators, I said that if you have a function like that, that equals the derivative of the gamma term with respect to x mu, and this becomes the derivative of the gamma term with respect to x nu. And this entire term is called the Riemann tensor. And you'll notice that it is made up of Christoffel symbols and derivatives of Christoffel symbols. It's called the Riemann tensor. I can tell you that for our purposes, it is also, and can be regarded as, the Ricci tensor, which we need. And that's why we needed to derive the Christoffel symbols, because as you can see, the Ricci tensor contains Christoffel symbols and derivatives of Christoffel symbols. And the Ricci tensor, remember, was the first term in the Einstein field equations, which I'm showing you now just to remind you. So what we've just shown is that the change in the vector, remember the angle of the vector rather than the length, is equal to dx mu dx nu times v times the commutator covariant nu covariant mu, and that term we said was the Riemann tensor, but for our purposes it's also the Ricci tensor. So let's just take stock of where we've got to. We've just shown that the Ricci tensor is made up of Christoffel symbols and the derivatives of Christoffel symbols. But what are Christoffel symbols? We'll go back to equation 9 and you see that Christoffel symbols are made up of metric tensors and the derivatives of metric tensors. And what are metric tensors? They can be thought of as the device that you need to correct for Pythagoras on a curved surface. Now what I can also tell you is that from the Ricci tensor, r mu nu, you can derive what is called a curvature scalar. It is simply a scalar. It is not a tensor, not a vector, just a scalar. Just as, for example, if you take the dot product of two vectors, you get a scalar. You can take the Ricci tensor and from it you can create a curvature scalar. The point about that is if the curvature scalar is not zero, then the surface is not flat. Okay, let's just review where we've got to. We've covered the metric tensor, g mu nu. We've covered the Ricci tensor, r mu nu, which includes a lot of Christoffel symbols. We've covered the curvature scalar, r. And so we've covered most of Einstein's field equations. There are just two more terms to go. The stress energy momentum tensor, T mu nu, and the cosmological constant, capital lambda. But first, time for another break. Okay, we're now ready to do the stress energy momentum tensor, T mu nu. What is the shortest distance between 2 points? Answer, a straight line. What is the shortest distance between 2 points, say, on the surface of a sphere? Not 2 points on a circle, but 2 points on the surface of a sphere. The answer is the shortest distance is what is called a geodesic. And on a sphere, on the Earth for example, the equator is a geodesic. Any line of longitude is a geodesic. The shortest distance between 2 points where you have to go round a curve, you can't go in a straight line, is called a geodesic. And we can define what's called a tangent vector, dx mu by d tau, as a rate of change of the distance that we travel with respect to time. I'm using tau because tau is what's called proper time. You can find out what proper time is from my videos on special relativity. The important point about proper time is it is the time which all observers, no matter what frame of reference they're in, can agree on. So if we use tau, we know that there can be no arguments about what we mean. So we're looking about the rate of change of distance with time, and that's called a tangent vector. And what we want to say is that the derivative of that tangent vector must equal 0 in order to find the minimum distance. So generally speaking, if you want to find the minimum in a curve, you take the derivative, you set that derivative equal to 0, and that will give you the minimum. It also gives you, incidentally, the maximum, but in this case we're talking about the minimum. So if you take the derivative of the tangent vector and set it to 0, you will get, as it were, the path for the geodesic, the shortest distance. Now, when I say take the derivative, remember we must always be cautious about derivatives in general relativity. We've already learnt that we can come a cropper if we take ordinary derivatives. We need to go for the covariant derivative. So let's take the covariant derivative of this tangent vector, dx mu by d tau. And from equation 7, which should be on the screen, you can see that that will essentially be the ordinary derivative plus a gamma term, which I won't fill out, but there is a gamma term. Remember, that's the correcting term. And what we can say is for the geodesic, this term must equal 0. So you've got this term plus this term equals 0. Let's look at this term here. This is essentially a double differential with respect to time. It is, if you like, d2x mu d tau squared. What does that look like? Isn't that acceleration? The rate of change of the rate of change of distance with time. d2x by dt squared is acceleration. And that equals, well, if that plus that equals 0, this equals minus the gamma term. Well, what does that look like? Let's remember that general relativity and Newton's law of gravitation need to be the same when you're just talking about ordinary masses, ordinary speeds, low speeds. You're not talking about black holes, because Newton's law of gravitation very nicely describes what appears to be gravity. And so in the simple case, general relativity and Newton's law must conform to the same thing. Newton's law says that force is mass times acceleration. Or if you like, that acceleration is a force term divided by mass. And here we've got an acceleration is equal to minus a gamma term. So what we can say is that that gamma term is the equivalent of force in Newton's laws. There'll be a mass term in it as well, but mass is constant, so let's forget about that. This gamma term, this Christoffel symbol, has a kind of broad equivalence to force. Now, to save time, I've just rewritten equation 9 that we derived for the Christoffel symbol. And remember we said that it consists of metric tensor plus derivatives of the metric tensor. Now let's consider a situation where we're talking about low gravity, low speed. We're not in black holes, we're not anything like that. It's just ordinary space, slow movement. General relativity must reduce to Newtonian gravity. When that happens, g becomes 1. And the derivative terms are very, very small with one exception, and that is the time term. And time, remember, has mu and nu equal to 0. So the dGOO, or 00 by dx time component, is the only term in the derivatives that has any significance. All the rest, when you're talking about slow speed, small masses, no black holes, all these other terms are very, very small. The only one that has any significance is the time term. And this term g becomes 1. And so that gamma term reduces to a half. That g becomes 1, so we can ignore that, multiplied by all of this lot, which is simply dg 00 by dx. And that, we said, was equivalent to a force term. So the force is kind of equivalent to this term here. But in Newtonian mechanics, force is minus the derivative of the potential. For example, if the potential energy near the Earth is equal to mgx, where x is the height above the Earth, then the force, it will usually be given as minus mgx, of course, then the force will be minus d phi by dx, which equals minus mg. The minus term simply indicates that the force is acting in one direction, but x is measured in the other direction. So all I'm showing here is that in Newtonian mechanics, force is minus the derivative of the potential. Now, we just showed that the Christoffel symbol, capital gamma, is the equivalent of a force term, and in ordinary space, where we're not anywhere near black holes, that it equaled the derivative of the time component of the metric tensor with respect to x. And we've also just shown that force is minus the potential, or the derivative of the potential, with respect to x. And so we can see that if gamma is a force term, that these two terms are broadly equivalent. And thus you get that g naught naught is equal to 2 phi plus a constant from the integration that you need to do. But you can forget all about the constant, because as soon as we differentiate again, that constant will go. There is probably a minus sign in there somewhere, but we don't need to worry too much about that either. We're looking at the principle here. What we're saying is that because the Christoffel symbol equals that, and Christoffel symbol has a kind of force equivalence, and in Newtonian mechanics, force is equal to minus the differential of the potential energy, that you can therefore equate these two terms. And if you equate those two terms, essentially the metric tensor, or the time value of the metric tensor, is equal to 2 times the potential energy plus a constant. Now, we've said that force is minus d phi by dx, but of course we really need to do that in 3 dimensions, and so that normally reduces to what is called the divergence of phi, where the divergence term is simply a d by dx plus a d by dy plus a d by dz term. And that, of course, should be minus there. But we also know from Newton's law of gravitation that the force is equal to minus g, the gravitational constant, times the mass of one object times the mass of the other object divided by the square of the distance between them. So let's consider an object of mass m, and let's consider a distance r from mass m. And we ask ourselves the question, what is the force acting on a unit mass placed a distance r from m? Well, if the unit mass, that means the unit mass is 1, the force will be minus gm over r squared, because m is 1. What is therefore the force capability across the whole of that surface of that sphere? Well, that's going to be the integral of f dA, where dA is the area of the surface of the sphere. And that's going to be the integral of the force, which is minus gm over r squared, times dA. Well, if you integrate out, that of course is simply going to be equal to minus gm over r squared times the entire area of the surface of that sphere of radius r, which is 4 pi r squared. The r squareds cancel, and so you find that that reduces to minus gm times 4 pi. Now there is a theorem called the divergence theorem, which I won't derive, but you can look it up. I'll write it out first. It says that the integral of f dA over an area is equal to the integral over the volume of del f dv. And what that means in layman's terms is that the outward flux through the area of a sphere is equal to the volume integral of the divergence of the force. That's just a divergence theorem that can be derived, and you can look it up. I also just want to remind you that density is mass divided by volume, and that therefore you can say that the mass of an object will be the integral of the density with respect to volume. So now I'm going to take f dot dA, which we calculated to be this term, and set it equal to this term. So you've now got that f dot dA is 4 pi g times m, or more accurately minus 4 pi g times m, but for m I'm going to use the integral of rho dv, density times volume. That's f dot dA, or more accurately this is the integral of f dot dA, and that's going to be the integral of the volume of df dv, or del f dv, the divergence of f. Well, although it's not really proper to do it, you can cancel out the dv's. Essentially what you're left with is that del f, the divergence of f, is equal to 4 pi g rho. Actually minus 4 pi g. Unfortunately, I had a camera failure for the next section, so I'm just repeating the flow of the argument. We've shown that the force is minus the derivative of the potential in Newtonian mechanics. We've also just shown that the derivative of the force is equal to minus 4 pi g rho. Consequently, if the force is minus the derivative of phi, the derivative of force is the derivative of minus the derivative of phi, and that equals minus 4 pi g rho. In other words, minus the derivative squared of phi, the potential, equals 4 pi g rho. The minuses on both sides cancel. Earlier we showed that the time component of the metric tensor g00 equals twice the potential plus a constant, which means that the potential is half the metric tensor. I've dropped the constant, but you'll see there's no problem about doing so, because as soon as you do a derivative of phi, derivative squared of phi, which is this term here, replacing phi by half g00, the constants will all go, of course. So now you've got that the derivative squared of phi is 4 pi g rho, so the derivative squared of half the time component of the metric tensor equals 4 pi g rho, and if you multiply both sides of the equation by 2, you get that the derivative squared of the metric tensor equals 8 pi g rho. The problem with that is it's not a tensor equation, and for general relativity we need tensor equations. So what we're looking for is something that looks similar to it, but where on the left hand side of the equation you've got a tensor, and on the right hand side of the equation you've got a tensor. So we want something that has the form of g mu nu, which is actually called Einstein's tensor, is equal to 8 pi g, but instead of having the mass density term rho, we want a tensor for energy, something that contains all the mass, energy, stress, pressure terms that you can have. So we've essentially got to find something for this and something for that. Well, let's look at the T mu nu side of it first. If you go back to my video on special relativity E equals mc squared part 5 and go to the point in the video which is 2 minutes and 10 seconds in, you'll find that we derive what is called a momentum 4 vector. The 4 vectors, of course, 1 dimension of time, 3 dimensions of space. And you'll find that we define that momentum 4 vector as being mass multiplied by x0 over tau, x1 over tau, x2 over tau, and x3 over tau. And this is simply, obviously, that's the time component, the x component, the y component, and the z component in the 4 dimensions of space-time, divided by tau, the proper time, the time that everybody agrees. And what we showed was that if you reduce this term, you get essentially an mc squared, which is energy, E equals mc squared. And these terms all effectively become the momentum in the different coordinates. So it's mv in the x direction, mv in the y direction, and mv in the z direction. So this 4 momentum reduces out to basic rest mass energy plus momenta in the 3 coordinates of space. Well, that's fine, but that is just, of course, essentially a vector. We need a tensor. We need not p, but t mu nu. And that means we need a 4 by 4 matrix. And to save time, I've drawn one. And there it is. You will see that t has all the values of mu and nu from 0 to 3. And what do all these values mean? Well, the top one, t0, 0, that is going to be the time component of the energy, stress, energy, momentum tensor, and that has this kind of equivalence. It's the energy part of the tensor. The 3 components along the top here are what are called the energy flow parts of the tensor. The 3 components here are what are called the momentum density of the tensor, and the 9 components which are left are essentially the momentum, flux, stress, pressure parts of the tensor. In other words, we are embodying every part of energy that we can think of, whether it be pure energy, rest mass energy, momentum, stress, all of it somehow finds a place in this stress, energy, momentum tensor. It is, if you like, a measure of energy per unit volume. Now, energy has the same units as work, so we can think of this as work per unit volume. Work is force times distance. Distance is a length. Volume is a length cubed. So that's equivalent to force divided by a length squared, which is force over area, which is, of course, the units of pressure. So that's how energy per unit volume can also embrace pressure or stress. So that's given us, we can't derive it, but I'm trying to illustrate how we get here. That's given us a stress energy momentum tensor with 16 different terms, some of which it turns out are duplicates. It comes in the form of a matrix. It embodies all forms of energy, and it's the stress energy momentum tensor that we use on the right hand side of the Einstein field equation. So now we've got, on the right hand side, we've got the 8 pi g that we derived, but we're going to replace the density term that we came up with this new stress energy momentum tensor, and we're going to have something on the left hand side. Now what could it be? This is, as it were, the mass term. On this side we need something that is the space-time curvature term. So Einstein thought that the obvious candidate for it would be the Ricci curvature tensor, R mu nu. But there's a problem. The problem is that we have a thing called energy conservation. Energy can be neither created nor destroyed. So if you take the derivative of the energy tensor, it should be 0. There is no change in energy. The problem is, if you take the derivative of the Ricci tensor, it does not equal 0. So that equation can't be true, because the derivative of one side would be 0, the derivative of the other side would not. Now, bear in mind that we must always, when we're talking about general relativity and field equations, never do ordinary derivatives. You will come unstuck. We must always use the covariant derivative. So if we've got that the covariant derivative of the energy side is 0, we need something on the left-hand side whose derivative will equal 0. Now what Einstein actually found was that the covariant derivative of the Ricci tensor was not 0, but it actually was 1/2 times the covariant derivative of the metric tensor times the curvature scalar, which we spoke about earlier. If you've got an equation like that, you can bring everything to one side, and essentially you get that the covariant derivative of the Ricci tensor minus 1/2 times the metric tensor times the curvature scalar equals 0. And now we've got a covariant derivative of a term which equals 0. We've got the covariant derivative of TMV equals 0, and the covariant derivative of this term equals 0. Therefore, that term and that term must be equivalent. And so we've now got a left-hand side of the equation, R mu nu minus 1/2 G mu nu times R, equals the right-hand side of the equation. Well, it's not just T mu nu, of course. It's 8 pi G T mu nu. And we're almost there. It turns out for dimensional purposes you need to have a c to the 4th term here, but that's essentially just a constant for dimensional purposes. But Einstein realised he'd forgotten something. You remember that earlier we showed that the covariant derivative of the metric tensor equals 0, because it did it in one frame and therefore it must do it in all frames. And therefore we could have included the metric tensor in this equation here, not just as a multiplier of r, but in its own right. And of course we could have included it with any constant in front of it. So Einstein therefore decided that you needed to include this term in this equation again. So now you need R mu nu minus 1/2 G mu nu R, which is this, just this term here. And now you need to include the fact that you could have had a metric tensor term in here. So we'll add it. And we will have a constant which we'll call capital lambda multiplied by the metric tensor, and that equals 8 pi G T mu nu divided by c to the 4th. This part, you'll remember, was the Einstein tensor G mu nu. What is this capital lambda term? Well, it's called the cosmological constant, and curiously it is the constant which Einstein first thought of way back when he was trying to identify how you could describe space in mathematical terms. Now, he was being told at the time that space was fixed and unchanging, that nothing moved in space if you looked at it over a huge cosmological time and space frame. Obviously, the Earth goes around the sun, but generally speaking, everything stays as it is. That's what people thought. And Einstein said, well, that can't be right because gravity would tend to make all the galaxies pull together. And if I'm being told that they are not pulling together, there must be something which is balancing gravity and pushing the galaxies apart, so that gravitational attraction is being balanced by the thing that's pushing them apart. And he found that you could reintroduce that into his Einstein field equations as the constant that you multiplied by the metric tensor. This term is a very, very small term, and you will often find it will be left out of the Einstein field equations. It only becomes relevant when you're talking about major cosmological scales. And that's it. We have derived, in sorts, the Einstein field equations. Just to remind you, mu and nu are of course the time and space dimensions, 0, 1, 2 and 3, and therefore there are 16 equations there, but 6 of them are identical to another 6, so it reduces to just 10. If you want more information, I remind you that Professor Leonard Susskind of Stanford University gave an excellent series in 2008, and I gave you the link to that at the beginning of this video. That's it. We're done. The Einstein field equations for beginners.